In this video, we're going to begin to look at the idea of complex numbers. You're all used to real numbers. Okay, there's the set of complex numbers as well. Now, in the 18th century, a solution was found to the equation x squared minus 1. The solution was this imaginary number I is the square root of minus 1. All right, and or I squared is -1. Now, the thing about this is, when it was initially found, nobody knew what to do with it. It was this strange object. But of course, complex numbers now become absolutely essential to fluid dynamics, aerodynamics. These whole areas operate on it. So they make use of complex functions and so on. So what was not understood in the 18th century now has, 20th century and 19th century onwards and so on, has found considerable use. Air under pressure at very high speed behaves like a fluid, and the mathematics of fluids is involving complex variables. Okay, so a complex number has the form z equals a plus bi, where a and b belong to the real numbers, right? So they are real numbers. Okay, we also say that the real part of z is a and the imaginary part of z is b. Some properties of the complex numbers. Well, addition. The addition of two complex numbers, you add the real parts together and you add the imaginary parts together. Okay, same with subtraction. You subtract the real parts from each other and the imaginary parts from each other. Multiplication by a scalar, k times z is just k times a whole lot, so k times a, k times the real part plus k times the imaginary part, where k belongs to the reals. Multiplication of two complex numbers is carried out in the following way: a plus bi times the second complex number c plus di, expanded out as you normally would. Expand out the parentheses, you get a times c, adi plus bci plus bdi squared. Okay, I squared, as we saw, is -1. So this AC is now grouped with this. Now BD becomes minus BD, so the real part here becomes AC minus BD, and then the imaginary part becomes AD plus BC multiplied by I. So two complex numbers multiplied together give us this result here. All right. Okay, we can represent complex numbers on the Argan diagram. Okay, the Argan diagram has a real axis. The real part of z is the horizontal axis, the real part of the complex number plotted along the horizontal axis, and the imaginary part plotted along the vertical axis. And this is the Argan diagram. Okay, so for instance, the point 3 plus 3i has real part 3, imaginary part 3i. It's this point here. Okay, a plus bi goes wherever. If you have point z, okay, let me just show you one more. -4 plus I is over here. Real part's -4. Imaginary part's plus I. That goes over here. A plus bi. Okay, if we were now to plot that, we get some point in the first quadrant. If we let z equals a plus bi, we get some point in the first quadrant. Then if we multiply both sides here by I, so z times I, and then all of this times I, so we get ai minus, remember, I times I here is -1, so we get minus b, so we get ai minus b. Well, we can see that now becomes in the second quadrant. If we multiply this result now by I squared, we get z times I squared. Okay, so if we multiply this here by I, that bit there, I, we're going to have -a minus bi, -a minus bi, which you can see is in the third quadrant, just down here. If we multiply again, as you can predict, we're going to end up in the next quadrant. So if we multiply zi squared by another I, so we get zi cubed, then we get -a times I, and then we have I times I squared is -1, -1 times minus b is plus b, so we get b minus ai, which places us in the fourth quadrant. Okay, and the pattern then repeats itself again if you keep multiplying by I. Let's have a look at the square root of 16. We can write that as square root of 16 times square root of -1, so that becomes 4i. So the square root negative 16 is just the complex number for I. Z1 times Z2, if we had 1 plus I times 3 minus 2I, expand that out as we did above, we end up with 3 minus 2I plus 3I minus 2I squared. I squared is negative 1, so we have 3 minus 2I plus 3I gives us plus I, 3 plus I, minus 2 times negative 1, so it's plus 2, so that gives us 5 plus I. All right. So introduction here to complex numbers. That part was hidden a moment ago. Can I just point, every time we multiply by the number I, so we take the complex number z equals a plus bi, every time we multiply by I, we are rotating the complex number z through 90 degrees in an anti-clockwise direction, as I was showing before. Okay, let's have a look at the sets of numbers. All right, so we start with the natural numbers. Okay, all the counting numbers, 0, 1, 2, 3, 4, 5, natural numbers. Then we include the integers. Okay, Z, natural numbers are a subset of the integers because the integers include the negatives. The integers and the natural numbers are a subset of the rational numbers. Okay, remember whole numbers over whole numbers, integers over integers. Okay, and then the rationals are a subset of the real numbers because real numbers include things like pi and recurring decimals and all the rest of it. Okay, and transcendental numbers and all the rest of it. And then the real numbers themselves are just a subset of the complex numbers. Okay, because remember, a complex number has a real part and an imaginary part, and so the real numbers are really just a subset of the complex numbers. The largest, the biggest set, if you like, is the complex number set. All right, and that's it.